right, so let's see. Moving from anomalies to known phenomenon. I think, why did I pick that title? After doing a lot of anomaly detection, algorithms and applications, I concluded that the goal should be to not do any anomaly detection. We should try to get away from that altogether. So what does that mean? Why am I standing here if I don't want to do anomaly detection? The reason is because anomalies are very overwhelming in practice. The real goal is to, every time you see these things, figure out what they are and label them so that you can start recognizing them. And eventually you recognize everything you see and nothing's an anomaly anymore. Of course, that's an unachievable goal, but I think that's the goal we should all be striving for. So anyway, with that, let me give you a little background. So, you know, what am I interested in right now? So currently, I'm on a leave of absence with Uber Advanced Technology Center, and we're working on vehicle technologies, mapping, safety, and autonomy. And so that's what anomalies in that area are what I'm excited about. So I'm going to start by giving you just a little bit of historical background on self-driving vehicles leading up to where we are now and what we would like to do with them. So, okay, so here's a very old picture. This one is from the 80s, right? This is NavLab. It's a giant van. And the reason it's that big, and it is self-driving, the reason it's that big is because it takes that much space to house all the computers that drive this thing. And of course, in this particular case, the anomaly is when it actually does something right. And so, this is really the in some way the golden age of robotics, where the rule was keep the video camera on in case something good happens, right? And so, but this is the very start here. Now, in some ways, that effort culminated's the wrong word, but that effort led to the No Hands Across America drive. So that happened in 1995. It's hard to believe that was over 20 years ago. But what that was this vehicle drove from Pittsburgh to LA over 98% autonomously, and its longest no-hand stretch was 70 miles. Now this vehicle was pretty simple. It was just image-based, just a camera in the front. And it didn't really know what it was doing. It just knew what a lane was, and it knew how to aim at the middle of it. And what else is interesting about this vehicle was it used a multi-layer perceptron, which you might recognize as a word that was used in the previous incarnation of deep learning. And so it's interesting that the deep learning booms and busts have taken a whole cycle over the period that people have been looking at self-driving cars. Okay, so what came after that? Well, after that success, CMU moved on to some more complex things. So this is Crusher. This is more of an off-road vehicle. And it's got some nice new features. One is it knows where it is and where it's trying to go. It's got GPS, and so it's trying to navigate. It has some LiDAR to go along with its cameras, and it can actually sense objects. Doesn't know anything about them, doesn't know what they're going to do. It thinks they're just static blocks like a block world. But it does sense the objects, and it tries to find its way around them while it's trying to get to its goal location. So that's a nice step forward. So this line of work, in many ways, culminated, although again that's the wrong word, in the DARPA Urban Challenge. And so this was the DARPA-sponsored event. Where vehicles all came out in a mock city to try to drive around. And what were the improvements here? Well, now there are good maps. So these vehicles have a three-dimensional map of what's going on out there, and they can use that to help them get around and understand what challenges they're going to be faced with. They also reason about the other vehicles. And so they're not just static objects out there, they're actors that they can reason about. And of course, these vehicles, many of them are heavily based on LiDAR, and Velodyne's in particular. And of course, the most important thing here is that CMU wins. That's the big news. But the real most important thing, I think, looking at the bigger picture, is it was at this stage that Google decided the technology was there. So they looked at what the CMU team did and many of the other teams that did well in this contest, which is essentially just what I put here in these bullet points. And they said, this has some potential, we can do something with this, and they started the Google car project at this point with many of the participants in this contest. Of course, CMU also saw the potential of this technology, and one of the things they went on to do was to develop a commercial system with Caterpillar to drive this truck around in mines. They did several other things, which I don't have videos for, but working with, say, tractor manufacturers and other things for automated agriculture. And so what's the goal here? Well, the real goal is sort of safety, efficiency, preventing mistakes. These are based on Velodyne and radar. And, you know, the safety issue is kind of funny, right? There aren't that many of these trucks. It certainly doesn't cost that much to have drivers in them all. But it's really the safety that's the problem. Because if you have a little Ford pickup truck, for example, and you drive over something you shouldn't, it probably puts a hole in your tire, and then you have to get a new tire. Well, in this thing, if it drives over something it shouldn't, it was probably that Ford pickup truck. And these tires are much more expensive. So this was quite a win for this particular system. Okay, scroll forward to the near present here. So last year in January, Uber opened the Advanced Technology Center in Pittsburgh to work on mapping safety and autonomy. And so many of the people that were involved in those previous projects have joined Uber to work on this. This, of course, is our car. For those of you that are around Pittsburgh, you'll see these driving around quite a bit. And so you can see it has the LiDAR sensor on top. It's got cameras all around it. It's also got things you can't see, the radar, the GPS, the IMU, all those things are there as well. And so the result is you have something that generates a ton of data. And so now what I'm going to do is I'm going to show you a video that in any other context would be relatively boring. This is just a video driving around. This is what we want this car to do. And it's just regular driving, but since I joined ATC, this video is terrifying because I look at this and it's absolute chaos. There's pedestrians everywhere, there's bikes everywhere, there's all these random markings all over the road. Some of them matter, some of them don't matter. There's things in the sky, some of those matter, some of them don't matter. All kinds of other objects on all sides of view and actors going all different directions. And somehow you've got to get through all of that and do the right thing. And so this is what now motivates me and my interest in anomaly detection. And so let's go on now. What? Is that a video of a human driving? That's a human driving, yes. I would love to tell you, oh yeah, that's nothing. Those are the easy ones. No, that's a human driving. And so what are the questions I would like to answer here? One is about the external environment. Has this vehicle encountered anything unusual? But of course, really, I don't want to see unusual things. I want things that I know. So do I already know what this is? And of course, how unusual is it? Maybe I've never seen it before, maybe not, but I want to know is, the real question is, am I ever going to see this again? Do I have to solve this problem or not? You know, if I see a pterodactyl, well, maybe it's okay if I don't learn how to deal with pterodactyls. Maybe I'll be fine. Then the other one is more the internal one. Has this vehicle acted any different than it used to act? Do I already know why it didn't act differently? And of course, a very big one is the issue only with this car, or are somehow all my cars doing this? That's another very important one. And so overall, it's really what is the underlying phenomenon and what should I do about it? So these are the questions I'm after. And let me now, I'll just scroll through some approaches and what I find interesting here. And so I'll go through just three things, sort of a classical single point anomaly detection, looking at groups of data points, and then finally this thing that I put the title of the talk on. Okay. So I think we all know what we mean by anomaly detection here, but there are a lot of methods out here, so I'm just going to put up a couple of slides to just to ground where I think about this from. So I think about it in the sense of the example here. So you've got some data that you're going to declare your typical data. You're going to fit some kind of model to it. In this case, maybe it's just a Gaussian distribution. But this should be some sort of model that has a decent probabilistic interpretation to it so that you can look at new points. And when new points come by that are of low likelihood, those are the ones you're going to flag as anomalous. So that's I know there's nothing new here. That's the framework many people in this room use. But just to show you, that's the one I'm thinking about. Of course, things can get a little bit more complicated than that. It doesn't, there we are. Some distributions aren't nice and parametric, so we often have to come up with more complex models for that. For example, non-parametric ones. Of course, we're all familiar with this. And this one, I do like this one just because we use the phrase outlier right in the title of the workshop, but maybe outlier is not really the phrase that we want to use here, because this is an example that has anomalous inliers, right? They're well within the distribution, but they're still rare, and those are things we're interested in as well. What else happens to us? Well, let's see. We, of course, a lot of these models aren't very good in high dimensions. And so, again, nothing new here, but there's many things you can do to build your models that'll operate better in higher dimensions. You can decompose them in ways like with Bayes nets, or maybe reduce them with PCA, or maybe you're a deep learning person who likes to use those to represent your distributions. And of course, the one that doesn't get talked about a lot, but is maybe the most common one in use in industry, is feature engineering, right? You just you invent the features that you care about. And then the same thing happens after that. You build some kind of model and you just flag the low likelihood points. So this is the sort of idea I'm looking at. Now, most of the examples that are significant, I find, are not these single point anomalies in this sense. Really, we're looking for important phenomenon. Unless you really are a particle physicist or something, that gamma ray that went through and nuked something, you don't care. You're just going to go on, and maybe it'll happen again sometime, maybe it won't. What you're really looking for is anomalies that you need to be concerned with, and that's those larger scale phenomenon. You want to look at more information. So how do we do that? Well, one way we can do that is just to take the algorithms we have that typically would operate on sort of finite dimensional data points, and we can just extend them so that they operate themselves on sets or distributions of data. So that now what you're doing is anomaly detection on a subset of data rather than on a single record. And so, of course, the most common way, and this is also not new, right? Many people do this. And of course, our favorite way to do that, again, is the handcrafted features. Look at the problem and invent some features that we think will be important for recognizing the anomalies. But of course, it would be nice to have something a little bit more general purpose than that. So one of the things we do is look at, how can we take these complex objects and somehow break them into pieces that are more manageable. So one way to do that is exactly that, to chop them into pieces and then represent that object as a distribution over smaller types of pieces. You can do that with images, but lots of other complex things fall into this category, that it has a natural decomposition into smaller parts, and you can talk about modeling the distribution rather than modeling a single finite dimensional point. Okay. Okay, so the goal is to go ahead and classify or test the anomalousness of some distributions of points. Here's an example here. Maybe you've got some training data with some positives and negatives, and you've got some test point, and you'll want to answer questions about, does that distribution of data, does it match one of my classes, or is it an anomaly? So this would be a typical thing. So we're interested in the distributions, but even we only have samples from the distribution, and we want to do that. And of course, as we all know well, many machine learning algorithms can be kernelized, and so you can use these as a way to do very flexible kinds of machine learning. So the question is, how would we do this with these types of data sets where we're going to break them into samples from distributions? So one way to do that, if you have your data broken down this way, so you're thinking about it as a distribution, you can just look at divergences between the distributions. So most people are familiar with KL divergence, but in fact, that's just one instance from many larger classes of distributions that you can look at. And of course, this has the very intuitive explanation here. If these two data sets overlap each other a lot, so that the distribution you would estimate from them are quite similar from each other, you get a very low divergence, and as they become much different, you get a high divergence. Okay, so that's great, but how are you going to estimate this thing from these sample sets here? It turns out, this is work from one of my colleagues from a few years ago. You can do a non-parametric estimation of divergence between these sample sets. And I'm not really going to talk you through all the math here. What I'm going to do instead, you can read that in the UAI paper if you're curious. What I'm going to do instead is just give you the concept behind how this non-parametric estimator of divergence works. And the concept is very simple. What you do is for every, just to set up here, so the blue and red data points there live in 2 dimensions, and the blue ones come from one distribution, and the red ones come from another distribution, and we want to understand whether these 2 distributions are similar to each other or not. So we're trying to compute the divergence between them. So the way this works is for every data point, you pick some k, maybe it's, whatever, 3, I forget what, 2, okay, it's 2 on the slide. You pick some k, and for every data point, you compute the distance to that second nearest neighbor within your own distribution, and you similarly compute the distance to your second nearest neighbor within the other distribution. And so you see them marked there, the second nearest neighbor in blue and red. So now you've computed this whole list of distances to nearest neighbors from all your points, from within distribution and to the other distribution. So it turns out that if these distributions are similar, these distances will commonly be similar to each other. And of course, if they're different, you'll commonly find that one of these numbers is really small while the other one is really large. And so that's the intuitive explanation for why that equation there is actually theoretically a consistent estimator for these divergences. And so that's what we're going to use to estimate divergences between distributions for which we don't know parametric families. So there's a really cool thing that happens now, which is lots of the kernels that we would like to use have a similar form to this estimator. And so the linear kernel, the polynomial, the Gaussian kernel, all these things can be written as these integrals over these distributions. And we just need to estimate these terms, p to the alpha, q to the beta. And it turns out that That's exactly the form of what we can estimate with this divergence here. So it's really nice that we now can estimate these kinds of kernels, and then we can go ahead and just plug them into any of our favorite kernel methods. There is one small problem here, maybe it's two. The problem is that having estimated this kernel, so those of you that are familiar with kernel methods, right, you build up this gram matrix. In this case, the gram matrix may not be PSD. And there's actually two reasons for that. One is that, except for special cases, using these divergences in this way, it's not a kernel anyway. Even if you knew the answer, it wouldn't necessarily be PSD. And of course, the other reason is that you have estimation error. You're estimating this just from sample sets. And so even in the cases where it really is a kernel, this estimation error itself may cause you some issues. Turns out, in practice, that's not a big deal. You just make it symmetric and then project it onto the cone of PSD matrices, and you're fine, and you just use it. It might not be, when I say, and sorry, when I say you're fine, what I mean by that is not that any theoretical result carries past doing this. I just mean that empirically, when you do this, you get good results from the algorithms. And you can read about that also in a paper in CVPR. Okay, and so this is just what I mentioned. Once you've done that, you can plug that kernel into any of your favorite kernel methods, and you can use that. For example, if you like SVMs, you can use it as a one-class SVM. We called it support distribution machine just for fun. Of course, there are other ways that you can make models of groups of data points. So if you think about graphical models and you think about topic models from text, of course, text has exactly this flavor, right? We commonly take text and turn it into bag of words or n-grams or anything, other kinds of representations, and just make topic models out of them. What's interesting is you can just take that same framework, all your favorite topic models, all the infinite number of variations of those, you can always just go to the bottom of those things and take out that last bit that is just that distribution over words, and you can swap in other kinds of distributions you're interested in. And now you have something that's a nice graphical model of distributions of whatever kinds of objects you're talking about. And so that's another method we've been exploring. Okay, I'm going to show you a couple things with images. So I think by now lots of people have pretty good knowledge of how images are processed, but just for fun, I'll do a little detour and just show you what you generally do to turn images into data points. And so there's an image on the right there, and we would like to make that into a data point. So the first thing is we do just what I was talking about. We chop it up. We make it into a whole bunch of little image patches. And now we can talk about this image as being a distribution over image patches. And so that puts us right in this framework I was talking about, that we can now compare two images as saying how related are these two distributions to each other. Now, of course, for each of those patches, metadata. You want to store whatever details you have about that image, where it came from, or even the position of the patches in some cases. But of course, then what do you ultimately do? You compute some features for those images. If you're a hardcore deep learning person, you use your favorite deep network to compute those features. If you're more of a classical person, you've probably got your favorite kind of filters you like to run over images. But you can just store raw pixels if you want and look at distributions of raw pixels, and you can make simple convolutional features by passing masks like edge detectors and other things over the images, and then you can aggregate them into histograms that count things like orientations and sizes of edges, and you can do it at many scales. And so this gives you this nice large dimensional vector that you can apply for each patch. And then if you look at the whole image, you've got a collection of these patches, and you can talk about the distribution of those patches in your image. Okay, so what happens? Here's just one example here. Here's a bunch of images. We do exactly that kind of operation on them. And then what I did here is I just sorted them by their anomaly score starting at the upper left. And what you can see is that there's actually 5 of these images that don't really belong in this set. These are all highway scenes, and there's 5 living rooms in there. So you see this kind of thing. You can pull out images pretty nicely doing exactly those kind of features, and then just doing the divergence estimation, and then running a one-class SVM on this to find the most interesting images in the set. Okay, let's go to something that's a little bit more fun, and that is we've done a lot of work with astronomers here. And so what are the objects they care about? Well, one of the things they care about is galaxy clusters. Those are some of the biggest objects that we know of, short of the universe, I guess. And what they want to do is find out where's an interesting galaxy cluster that might give me some new insight into physics. And so what we did is exactly this. So we have a spectrum from each galaxy, and now for a galaxy cluster, we can look at the distribution over spectra, and that will be a representation of that galaxy cluster. And so we can run exactly the kind of algorithm I described to you. And what's interesting, we went ahead and ran this, and so there were 505 galaxy clusters in the Sloan Digital Sky Survey that we looked at. And we pulled out the most anomalous one, and what we found out, I guess I should take a step back for those of you who are non-astrophysicists. If you wanted to make the coarsest possible description of the types of galaxies out there, there are blue galaxies that are young and have lots of stars and look like that one on the left, and there are red ones that are very old and tend to be elliptical, and many of their stars are dying. And then there's a few random ones that are irregular in there. So we ran this. The most anomalous galaxy cluster that came out was one that had a whole bunch of these blue galaxies and no red galaxies. And we looked at that and said, okay, I don't know, it's even got a couple of irregular ones, but it's not uncommon to see that. What's going on? And we sort of said, oh, okay, I guess the algorithm doesn't work. We showed it to some astrophysicists, and they said, oh yeah, that can't happen. It's the issue is that their understanding of how galaxy clusters are formed is that there are always some big old granddaddies in the middle that pulled all the other galaxies in, and because they're so old, they have to be red. And so there isn't any way to form, that they know of, to form a galaxy cluster that doesn't have any red galaxies in it. And so we thought that was pretty cool. We showed that to them, and I don't think we have the answer. Neither we nor they have the answer for how this particular galaxy cluster formed. But I thought it was a nice discovery from a distribution that was strange, even though none of the objects in the distribution were strange. Let's see. Let me, just skipping to some other scientific examples. Here's one where we looked at a turbulence simulation, and the same thing. What we can do is look at the velocity distributions. And so here the idea is that each one of those snapshots is a distribution of velocities. And we have some positive and negative ones, so we were doing some classification, but we also did some anomaly detection on this one. Here's an example, a 2D snapshot of this. We used it to find vortices. This is something they care about. They want to be able to enumerate how many and the locations and the changes in the vortices to understand their fluid dynamic simulation. So we wrote this for them to go through and find all the vortices in it. But we also found anomalies. And one of the strangest ones that came out was this one. It's a little hard to see what's going on here. Basically, there are a couple of vortices here, and they're a little bit anomalous, because they're not that common in the fluid. But what was really anomalous here and what's happening is this is a collision of two vortices. And so right there at the center, that was the thing that stood out from this. And that was something they were also quite interested in. I think what I'm going to do is skip over the boats. We'll get on to, okay. What I want to do, well, sorry, I'll tell you what the boats are. They're little environmental sensors. They're about this big. They go out autonomously and they measure all kinds of things in the water. And the goal is to travel around and look for phenomenon that are unusual, that may be water quality issues. I'm skipping over it because since then the guy who owns the boat has spun off a company and he's doing this commercially now. So, but let me just move on to this idea of moving from anomalies to classifying an automated response. So I'm gonna before I do that, I'm gonna get a little bit into another anomaly detection method that's pretty classical. It's a spatial scan statistic. And so the idea here is that you build a model for the data points over your whole data set, and then what you do is you choose some sort of subset shape like this ellipse here, and you shift that over the whole image, and everywhere in the data set you check how well the likelihood of things inside that region matches the overall likelihood for the whole data set. So could you model this data better as a single homogeneous data set, or could you model it better as a two-component data set where things inside that region are different? And so this is a very classical thing that's done. And right, so what do? You make tons of these regions, and then you check them all to see if any of them are different from the rest of the data set. That's implicitly what people tend to do in anomaly detection approaches anyway. Turns out you can also do a Bayesian form of this, which means you can start to recognize lots of classes, and so for every one of them you can talk about the probability that they belong to various classes you know about or none of them. So now I want to get to the application. This is a very old data set. This is pharmacy data. So we have all the over-the-counter pharmacy sales in 5 categories aggregated by zip code across the whole country. And so this data set very originally goes back to 911. So after 911 happened, there was a work in the area of biosurveillance. So the idea was that there was concern there would be an anthrax attack, and people were looking at ways to recognize it as early as possible. And the thinking was that, so anthrax, when you get anthrax, what happens is initially you feel like you've got a cold or the flu or something. Maybe you just go to the drugstore, and then a day or two later you feel fine, you think you've recovered, and then a day or two later you're dead. And so the idea was, well, if we could track some of these trips to the drugstore, we might notice if something's gone wrong. And so this is a classic anomaly detection example, right? You wanna watch the data and flag things that are wrong. And this, I'm going to show you something completely different with this data, but this was, again, one of my inspirations for why do we have to get away from anomalies and get to things we recognize? Because we fielded a similar system to this that was based on emergency room admissions and actually turned this on in the state of Pennsylvania. And the problem, it was useless. It was completely useless because it just generated way more anomalies than anyone could ever track down, and so nobody ever looked at them. And so I think, probably all of us here who have played with anomaly detection systems have had some version of that experience before. And so we said, okay, and especially for what this was targeting, bioterrorist attacks, it turns out, thankfully, there aren't too many of those around. And so you really put yourself in a tough spot asking someone to look at these things all day when there's never anything interesting in it, right? And so when we said, okay, but we still need to develop these methods what else can we do here? And so what we decided was, let's try to recognize some other phenomenon that would show up in this pharmacy data. And the one we sort of settled on was foul weather. And so here's an example. This is Hurricane Francis in 2004. And so it traveled from the Atlantic there over to Florida and then into Alabama and Georgia. Turns out that hurricanes affect over-the-counter drug sales. Pretty cool. When a hurricane is imminent, people go stock up on their supplies. When the hurricane arrives, people are barricaded at home waiting out the hurricane. Now, of course, we don't need this to recognize hurricanes, right? We have weathermen that are, they're pretty bad, but at least they have a tendency to recognize a hurricane when it's coming. So we don't need it for that, but it's great for us to try to test our anomaly detection algorithms and see if we can find the right things. Another idea we had is that this same curve, although this really is a learned curve about hurricanes, I'm pretty sure this exact same curve works for beer sales in Pittsburgh before a Steelers game. And so in fact, we even did that. We tried to recognize football games in the data, but it turned out that you need hourly data to really recognize that, and we only had daily data here. So, okay, so but this is quite a complex phenomenon, right? This is not a one person going in and buying cold medicine does not indicate a hurricane, right? Because this thing shifts in space and in time as the hurricane progresses. And so what we did, you can read about the model in Kostof's dissertation if you want. I'm not going to go into it, but basically we hacked up a special graphical model that would do this sort of spatial temporal representation of the categories of the drugs we have here in order to do all this. So then what did we do? We did anomaly detection. So we went ahead and here, this is on a loop. What this is just a plain anomaly detector, and what I've done is cut out the part of the country and the dates where this hurricane actually shows up. And so you can see the stuff when it loops around. You can see it in Florida here. There was also something in Texas. I don't know if that's also connected to the hurricane or not. What I should have is a little bit bigger picture of the U.S. is because what you would see is that there's all kinds of stuff going on. There's forest fires in the West. There's all kinds of marketing efforts that are causing sales to spike all over the place and data problems. And so there are tons of anomalies all over this data set. So it is exactly the problem I just described. And so we said, okay, but let's sort of walk through this. How would this system work, okay? Somebody sees these anomalies. They look at this and they say, okay, I figured it out. There was a hurricane that went through. So what we would like to do is say, okay, let's tag that. That's a hurricane. And in fact, that's what we did. We went ahead. We took the 10 zip codes right where the hurricane first hit, and then we did an iterative refitting of our model. So from those 10 zip codes, we learned a model of the event. Then we reapplied it to recognize the other zip codes that were affected, and we looped a couple of times to find all the things that were part of this event, the hurricane. And so having done that from one instance, we ran it. 2005 was a big year for hurricanes, so we ran it on the data for 2005. And what you'll see here is that it recognizes every single hurricane that came through in 2005 with only one false positive. That was the false positive right there. But you'll see the other hurricanes going through here, which I was quite pleased by that, because what this has done now for the unfortunate anomaly detection watcher, we've now just taken all these anomalies out of the picture for them and tagged them as hurricanes so they can just skip past them and they don't have to look at those anomalies anymore. Okay, so that's great. We've done some other things of a similar flavor. Let's see, I wonder if this is going to work. what we did is we set up a website for the astronomers. And so what they do, this is for the Sloan Digital Sky Survey. What they can do is log into this website. They can pick a type of object they're interested in. Here maybe they're interested in stars. And so they can grab all the objects that were there. And this is something that that was updated every morning from the telescope, so they could get up with their coffee if they wanted to see the most interesting things that showed up last night. And so the way this works is they can see the objects here, and then if they click on the object, it goes, uh-oh, I'm already, oh no, it worked, okay. This goes directly to the Sloan site, so they can see all the things about the object, and in particular, they can see the spectra here, which is of interest to them. And so the point of this system is to be exactly the same thing as the other one. What they do then, so here's a tag by Andy Connolly. He says this is, I think PN is like a planetary nebula. He says this one's a planetary nebula, and in this case, actually it's already a known one. So he actually wrote down the ID of that planetary nebula. These are indeed rare objects, but they aren't really ones that we want to show up here. We want to just tag them as planetary nebula. And so we built this website for the astronomers, and they go down and there's various other tags they put in here. They put comments and anything they put a tag on, then we can build a classifier for that tag. And what that allows them to do is, going back to the previous screen, they can then filter for objects they're interested in, ones that have certain tags or don't. I'm terrified to try to switch back to the other screen. We'll see what happens. Oh, I made it. Okay. All right, so I'm going to wrap up now, and what I'm going to do is just come back to that very original problem, which is the cars driving around, right? And so what we've done is architected our own anomaly detection system at ATC. This is a kind of a box diagram of it. The idea is that you get logs that come from the car. You can build data models of those logs, things that represent what's usually in there. You run those through anomaly detection. That pulls anomalies out. And then you can pass the anomalies on to humans to label them. And then the idea is you classify them after that, again, with this goal of getting rid of the anomalies because we don't want to look at them anyway. And so what is an example of what that looks like? So what you're looking at here, this is, in the middle of that picture is a car. Those are the LiDAR stripes around it. Those other objects are other cars. And so the idea is to automate all of this, right? And so what's happened here, it's been recognized that this is an anomaly because it's a hard brake. So cars, most of the time, don't press their brakes. And so here's an instance where the brake was pressed hard, and we want to know why. And so it turns out in this particular case, and this has been automated now, so this is our system putting that label in there automated. I don't know if the print's large enough for you to see, but basically there was a car in our lane, and so that's what caused this event. And we've now tagged it as that's why it happened. And so this is the kind of system we have and what we're pursuing to get toward our goal of that video I showed you at the beginning being an actual real video and being a real video that has no anomalies, because everything that happens, even if it looks crazy, we already know what it is. And so with that, I think I'll just wrap up here. I think it's important to set up the pipelines that go from anomalies to known events. Uber is hiring. I think that goes without saying, but I'll say it anyway. And with that, I'll stop and take any questions.
Thank you. One of the blocks in your architecture here for whole framework does say anomaly detection and feature extraction. Very often you don't know what features are important for anomaly detection.
Mm-hmm.
How you figure out that problem? Are you just finding anomalies anyway, and then you do feature selection in classification process, or you're approaching some other way?
Yeah, that box is just an admission that although I made fun of handcrafted features, and although I proposed something that would try to turn things into distributions so that you would have just distributions of points, that was just an admission that we're not there yet either. There are plenty of features that we just add to the list. We're like, yep, this is one we care about.
Yeah, because very often irrelevant features can basically hurt your prediction, actually.
Sorry?
Very often those irrelevant features can actually give you the wrong lead.
Right, yep. And that's definitely an issue here. Yeah.
Okay. Thank you.
Just a quick logistic announcement. If you have questions, please come over to the front so that we don't need to keep running around.
Thank you. I'm wondering what if the distribution changes over time? Because
Yeah,
oftentimes that's the case.
Yeah, I think.
Thank you.
I think it's almost certain that will happen. I think this is a very common problem in anomaly detection, and I would say we don't have any magic bullets for that one. We're going to do the usual things that we do. That we're going to move our baselines over time so that we're tracking relative to recent events rather than events that are older. I know many people do work in that area, and we're certainly interested in all the clever ideas that you guys have for that problem.
Thank you, Jeff, for the wonderful talk. So you talked about a lot of true positives and really learning from the real signal and building models around that. So don't we run into the risk of overfitting to the known anomalies, and wouldn't it be meaningful to learn from the negative feedback and just suppress what is not interesting, but really continue to be able to find unknown anomalies?
By negative feedback, do you mean like false positives or?
False positives in the sense, but this is not an anomaly, so we could just suppress them in the future.
Right.
Remaining to be able to detect unknown things. Because in the previous case, it appears that we may be overfitting to just the known anomalies, or what are your thoughts? Because it seems like it trade-off between false positives and false negatives.
Yeah, I think there are real issues there. Our approach for this is even the false positives, we're just going to make them another class. So if someone looks at this and says, that's a false positive, I'm not interested in that, we'll just tag it as that. And when that happens again in the future, it'll get that tag. What you said, I think, is a big risk of that, and it's one we're working on. How do you do that without risking that you completely paper over the anomaly detector and it doesn't hide one that matters? I think that's a real problem. Yeah.
Thank you.
Questions?
How you distinguish between what the anomaly and general trend? Just give you an example, especially in stock market, 2-3 weeks ago we had great exit. Okay,
Yeah.
So 2-3 days stock went down. That was an anomaly. But how we distinguish that one from a general trend going down, then you can sell your stock and not losing money.
Yeah, I think I think this is a pretty common problem in anomaly detection, and it relates to the question about what do you do about things that change over time. There's the long-term trends again, and we're not at least with the system we're putting together at ATC. We don't have a clever answer to that, so I'm happy to hear clever answers. But basically, the things that are long-term trends will be robust to them just by baselining off of moving our baseline along with the current data. Things that are shorter-term trends are essentially going to show up as anomalies until and if we can learn to recognize them as tagged trends that sometimes happen that we don't want to look at.
We have time for a couple more questions. No? Question there? I actually have one question. So you mentioned using Bayesian networks as like a useful approach. Could you give an example where Bayesian nets have been sort of used successfully for anomaly detection?
Oh yeah, we were. There was older work where we were modeling individual stars and galaxies using Bayesian networks. So we looked at the properties of the stars, things like its distance, its color, its temperature, those kinds of things, and the relationship between them. We modeled those just as a Bayesian net and used it to find anomalies of stars and of individual stars and individual galaxies that way, and that seemed to be an effective way to manage, a dimensionality that's a little larger than what we could do with just a simple non-parametric model.
Thank you. So any last question? Going once, going twice. All right. Please give a big round of applause to Dr. Schneider.